Welcome again in next ADASH video. In this one we will talk about frequency range of accelerometers and about usual mistakes in understanding of that. This is a most common accelerometer with 100 mV per G sensitivity. The frequency range declared by producer is from half Hz to 15 kHz with plus-minus 3 dB bias. Many people think that plus-minus 3 dB is not too much. If I ask them to convert this number to percentage, then they usually say it is plus-minus 3%. But it is not true. The plus-minus 3 dB is much more. Minus 3 dB is minus 30%. Plus 3 dB is plus 40%. Surprised? It means that the sensitivity on half Hz is only 70 mV. But the frequency range is not the primary subject of this video. Let's suppose the response function is flat. Most of the users want very low frequency limit. They say, I have to measure slow speed machine. They say, my machine speed is only 30 RPM. I need to measure on half Hz. If I ask them why, they do not answer. They do not understand this question. Let me tell you the example. If I want to measure the acceleration on low frequency, what acceleration level I can expect? Would be, for example, 1G? Most of the people are not able to imagine the vibrational acceleration and velocity. Everybody can imagine the displacement. When you say that machine vibrates plus-minus 3 mm, then everybody understands. On the picture is the old acceleration measurement instrument. It's purely mechanical. It was used 50 years ago for checking of car brakes. Now we are in the car. Now I push the brake pedal. You can see the reached level in meters per squared second. Please notice this mechanical pig-hold hand. And again in slow motion. It's nice, isn't it? But return back to the math formulas. We can use these formulas for conversion of acceleration to displacement and displacement to acceleration. Using this simple math, we can convert 1G to meters. If the speed is 30 RPM, it means half Hz. Do not forget, convert G to meters per square second firstly. The corresponding displacement level is 1 meter, not 1 millimeter, really 1 meter. No machine could work with such vibration level. The corresponding velocity level is 3200 millimeters per second. It is 125 inches per second. Impossible. I suppose the displacement level is 1 millimeter. The corresponding acceleration level is 0.01 meters per square second. It is 0.001 G. It is 1,000 of G. If the sensor sensitivity is 100 mV per G, then the voltage for 0.001 G is 0.1 mV. It is not too much. Can you measure such voltage level? The answer is no, because the usual sensor noise level in the field is from 0.2 to 0.4 mV. In such noise, it is very difficult to measure the 0.1 mV because it is lower level than the noise level. But let's go back to the basic question. Why to measure the amplitude on half Hz? The answer is simple. I would need it when I would want to balance the machine or investigate the looseness or misalignment. In these cases, I need to measure the level on speed frequency. But I do not know who wants to do it. When the speed is such low, then you should have the unbalanced mass tens of kilograms to increase the vibration level. The centrifugal force depends on power of speed. On 30 RPM, it will be very low. But the users say, no, I do not want to balance. I want to measure the condition of roller bearing. And this is the key point. For such measurement, I do not need the low frequency. When the ball is passing the scratches, or through bearing pittings, if you wish, on inner and outer races, then the shocks appear in time signal. The natural frequencies of shocks are very high, typically between 500 Hz and 25 kHz. We do not need to measure low frequencies. By the way, I suggest you to watch our previous video about low-speed bearing analysis using ACNT method. The next often misunderstandings are bearing fault frequencies. They can be very low for slow-speed machines, and users again use wrong rule. They say that the accelerometer has to be able to measure that frequencies. It is wrong. The fault frequency is the repeating frequency of shocks. It is not pure sine frequency which should be captured by sensor. We need to measure the natural frequencies of shocks. As I told you, they are higher than 500 Hz. On this picture you can see the time signal and its spectrum. The range is 25 kHz. All higher amplitude lines are in range 2 kHz and more. Please notice those very low G amplitudes. The spectrum displays the energy of signal. We see only shocks without significant energy in this signal. That is why the spectrum displays very low values. On this picture I measured spectrum in 25 Hz range only. Repeating frequency of shocks is around 1 Hz. You see nothing on 1 Hz. And again, notice very low acceleration level. The shocks do not contain energy. If I want to see the repeating frequencies in spectrum, then I must apply the demodulation. It means I must add the energy. Demodulated spectrum can display something visible. The demodulation spectrum uses the time signal which is enveloped. You can see the demod bandpass parameters. We want to measure only in band from 500 Hz to 25 kHz. We are not interested in low frequencies. You can imagine the enveloping like simple electrical circuit. The shock comes and charges the capacitor C. Then the capacitor is discharged through the resistor R. The discharging is much longer than the length of original shock. This is the additional energy which helps us in spectrum. And it really helped. You can see the repeating frequency 0.85 Hz and its harmonics. The harmonics always occur because the enveloped signal is distorted. It is not pure sine wave, which can display only one line in spectrum. All measurements have been made with ADAS VA4 Pro analyzer. Thank you for watching.